Ladies and gentlemen, what I'm holding in my hand here is an American wire gauge number 12 extension cord. You can see it's a little bit stiffer than most extension cords, but this is what you want to use when you're going to be making or doing a lot of work with construction tools. This will be able to hold a higher amperage, okay, before it wants to turn the breaker off, okay? We don't want to overload our circuits. Take a close look here. Of course, you can see that there's power here because there's a light. The reason why I want to show you this extension cord here, because we can actually see the connections in here as well. There's my green wire, which is the ground. It's going to the ground prong. And then here's an interesting fact. If you look over here on the side, we see a white wire. Now, our white wire, especially when we start talking about receptacles, it is going to it goes to the longer slot. The neutral, there's the white wire, is going to the long slot. You'll look over here, I've got the black wire, and it's going to the short slot. We'll learn more about that when we look at receptacles. This is a very economical tester right here. It doesn't cost that much at all. Very simple device. Of course, doesn't matter if I put the black wire in this hole or the black wire in this hole. And it doesn't matter if I put the red wire in this hole or the red wire in this hole. Simply all we want to see is the flow of power. Once I stick this, already we know that there's power because it's lit up there. But now we can simply see that there is a light on here indicating we got power. Again, when you're going to turn power off somewhere, you want to make sure the power is off. You can use a simple tester just like this one here. Test it somewhere where you know there's power, so you know it's functioning properly. Then put it where you need to turn the power off. You see it's functioning? Have someone, because you're not always going to be able to be in the same location, have somebody turn the breaker off. When that light goes off, you know the power is off. Now, don't simply just think the power is off. Do yourself a favor. Whoever turned the breaker off, tell them to turn it back on. We want to make sure it wasn't just you moving the tester. We want to make sure you still have good contact. So say, put the power back on. The light goes back on. Say, okay, turn it off. Okay, now you know the power is off. All right? Good tip, when you turn power off somewhere where you're working, put a piece of tape over the breaker that you turned off and put a note. Say, working on electricity, do not turn breaker on. Because sometimes you might have more than one trade working in a house. And they might not think of it. They are just doing their job and they need to plug something in and go, hey, wait a minute, no power here. They go down and they might turn the power on without you knowing it. So put a note always on the panel. Do not touch panel working on electrical. Fair enough? For your safety. Good little tip. So this is a very simple tester right here. This I can easily check 120 volts, no problem. Only meant for 120 volts. Let's take a look at one which is just a little bit better than that one there. Same concept, ladies and gentlemen. This one here, though, it will allow, if you take a look, it will allow me to test anywhere from 24 volts, low voltage, 48, 120, 240. Of course, we have other testers that can test for higher voltage. I'll show you one of those. I should have one of them on hand. Anyhow, that being said, ladies and gentlemen, same idea. I can either put these little tips on my contacts or I take these little sleeves off. You'll see we know we're working with 120 volts here. So when I plug this in, this particular one, it's going to light up to 120 volts. You can see over here, there you go. 24 volts, 48 volts, 120 volts. If I was testing 240, it would have lit up all the way to the top. Nice little tester right here. This tester here You do not want to have power connected when you're using this tester because you will hurt yourself. Okay, this is what we call a continuity tester. So, for example, sometimes when we make connections, we go from one box to another box to another box. Remember when we put wire nuts on our wires sometimes? Well, sometimes we can end up with a loose connection. So when I'm testing something, if I know I wired things properly, I turn the switch on, the light doesn't work. What's going on? The wires are connected properly on the switch. The wires are connected properly on the light. Now what I need to find out, is the wire broken somewhere, or is there a connection that is not connected properly? So when we do that, we are checking for continuity. So what we would do, for example, is on the one end, we're going to connect our wires together. On the other end, when we get to the other end where the light is or whatever we're needing to check, I'm going to put my connector on one side on one wire. Okay, I'm going to put my connector on one wire here, and then with the other side, I'm going to go to the other side here without power. There's no battery in this right now, so we won't be able to check. But when I do this, if that lights up, it's telling us everything is okay. The wires are connected from end to end. So you might have faulty equipment, but that's confirming if we have continuity. If that doesn't light up, there's a break somewhere in our connection. Now we need to go and find it. Another very important thing, ladies and gentlemen, when we make electrical connections, sometimes, for example, we may put an addition on a house. Never, ever, ever bury connections inside a wall, because if they become loose, nobody is going to find them. Wherever you make connections, of course, myself personally, when and if I have to do that, I like to do it in a box where maybe there's a light fixture or something else that is functional. That way I don't see a blank cover plate in the middle of nowhere. But sometimes it happens. We always want to make sure we have a plate that we can expose that box to check our connections. Fair enough? Never bury anything in a wall. It's a fire hazard. And of course, if anything is loose, we're never going to find it. We talked about Klein Tools, good manufacturer of electrical tools. These are two testers, very similar. The only difference is this one will only allow me to test up to 240 volts. This one I can test up to 1,000 volts. Okay. This one also has a nice little flashlight. All right. So, with that being said, I don't have to make contact with my wires to check and see if there's power. Here, I'm going to just turn this one on. Again, with this, I can check low voltage or high voltage. Okay, if the battery's running low, but normally it will also beep. Okay, but you can see the light is showing red now, telling us that there's power. This is the power side. If I put it on the other side, it's not going to do anything at all because there's no power there. That's my neutral. That's my hot wire. Now, nice thing about this tool here, when I run my tester along the side, inside here, these wires are twisted together. So you'll find as I run it along, there will be spots where it's going to be red and spots where it will, wrong one, where it's just going to stay green. So you can see it's showing me this is live. So I can check just from the outside of this wire. Oh, that wire is live. Good tester. Here's another little tester here. If I just want to test receptacles, we plug this in. It will have a chart here, which is telling me if it's wired correctly, if the wires are reversed, if the ground is not connected, if the polarities are backwards. It will give me a variety of information. And of course, as we start to learn about different receptacles, there is two types of receptacles. One is called a GFCI and one is called an AFCI. This allows me, by pushing this button in, to test that function on those receptacles as well. So that's what that button's for. But this here, of course, if I plug this in, if you look at the bottom, it's going to show you if these two lights on this side go on, it's correct. So of course, because I wired this and I know it's correct, you'll see those two lights went on. So my connections were done properly. So very quickly in a home, I can plug this in my receptacles and see if they were wired properly. Another neat tester that I would have liked to show you, it's called a multi-tester or a multimeter. A multimeter allows me to check voltage, amperage, and also resistance. Good little tool to have as well. Of course, you can see I'm holding an extension cord here. Of course, when we buy extension cords or we have extension cords, you can have 10-foot extension cords, 20-foot, 30, 50, 100. For example, right here, what I've got here with me right now, this is a 50-foot extension cord. 12 gauge, not cheap, ladies and gentlemen. But when it comes to saving this extension cord or rolling it up, loop it. Look how easy it rolls up just by looping it like so, ladies and gentlemen. That will make your extension cord last a very long time. We are going to start to learn about receptacles now, ladies and gentlemen. So when we look at receptacles, these are traditional receptacles. Okay, here's another traditional receptacle. And this is what we would call a Decora receptacle. Most of you in your home will either have ivory colored receptacles or white. Of course, when we talk about receptacles, we can have a 15 amp receptacle or we can have a 20 amp receptacle. To make things safer and to make sure that we are utilizing our equipment properly, when we look at a 20 amp receptacle today, it's going to look like this one here. Again, when we look at the neutral side of our receptacle, that's the longer slot. If you look at the neutral on this one and the neutral on this one, that's just straight. This one is T-shaped. When you see a receptacle that the neutral is T-shaped like that, it's going to be a 20 amp receptacle. Fair enough? The receptacle over years, and we just started talking a bit about one right now, it has evolved. For example, if we go back to receptacles in a Century home, you won't even see a ground. You're just going to see two slots and they're going to be exactly the same size. While over the years, we noticed, hey, wait a minute, we need to make things safer so we don't get bad shocks, so we introduced the ground. So for quite a few years, we then had the ground, but both slots were the same size. Well, in the last 30 years or so, when we look at receptacles, the neutral slot is longer than the hot side. So this is the neutral, that is the hot. How did I know that without even looking at it from the front? As you can see, I'm on the back side of this receptacle. How do I know that this is the neutral side and that this is the hot side without even looking at it from the front? Well, I can tell from the screws. Okay, when we look at the screws, and I'm going to show you it, it's easier to see on this one right here. The screws on the neutral side of my receptacle are silver. The screws on the hot side are going to be brass colored or copper colored. So that is how I was able to determine from the back which side is my neutral and which side is my hot. Fair enough? Now, again, as long as the power flows in and flows out, remember that circuit needs to be closed, power in, neutral comes back. Well, yes, power will flow in either direction, but there is a lot of equipment out there today that if the power is not flowing in the proper direction and we get a power surge, we can damage the equipment. So if we look at most receptacles and plugs today, let me grab a plug. Now, as you can see, let me grab this cord over here. You'll see on the plug, we got a skinny prong, and then this prong here is fatter. Okay, so the reason for that, ladies and gentlemen, if we were to follow this along, again, fat side, skinny side. The fat prong, if we follow this down, this wire going into my equipment is going to be the neutral. This one here is going to be the hot wire. That ensures that the power is going in the right direction and leaving in the right direction. Fair enough? And that's why, that is how we can keep our polarities straight. So we ensure the power is entering our equipment and leaving the equipment in the right direction. Years back, when we had plugs where the prong was the same size, I can put that plug in this way or this way, and it will still work. But if there is a surge in power, if that power is entering my equipment in the wrong direction, it might damage the insides of whatever I'm trying to power up. So to ensure we don't have any problems, we make sure that the polarities are correct. Fair enough? So we've got our polarities. Here's a simple little thing that I want to bring to our attention. Over here in Ontario, for the most part, it doesn't matter when you are installing a receptacle if you put it with the ground downwards like that or with the ground upwards like that. It doesn't matter, okay? There is no code in a residential environment that says this is right or this is right. You can put them in any direction if you choose to. But I will tell you this, for the most part, most electricians, including myself, like to put our receptacles in this orientation. Kind of looks like an inviting face. But if I was in, let's say, a factory or a warehouse and I'm dealing with a lot of explosive materials or combustible materials, including hospitals, ladies and gentlemen, where there's oxygen tanks and so on, the proper orientation in those environments is actually like so. Let me explain why. See, when you're working in those environments, ladies and gentlemen, and we plug something in. So when we plug this in, ladies and gents, and if it's not plugged in right away or all the way in, I probably have power. But imagine, if you will, maybe whatever I have plugged in is behind a desk and a paper clip should happen to fall off the desk. If that paper clip falls in between the plug and the receptacle, it's going to hit the ground first. It will ground out and nothing is going to happen. But if this is in this orientation and this paper clip should happen to fall in between, it's going to land on top of my neutral and hot. What's going to happen? Boom! It's going to spark. And when it sparks, if there's explosive materials, well, we can do some damage. So in those environments, there is actually an upside down and right side up, all right? But in a residential environment, it doesn't matter. For example, if you look over here, again, another perfect example of, you can see right over here. Let me see, I think I marked it over here. Here. UL. This has been inspected and approved by Underwriters Laboratories. If we look somewhere else on this, here we go right there. A little bit hard to see. CSA. So this has also been approved by Canadian Standards Association. So that's telling me, hey, this is a good piece of equipment to use. It's been approved by 2 safety approval markings. Fair enough? Also, when we are looking at our receptacles, very, very important, you can see over here in a circle, it says CU. In this circle, it says AL with a line through it. That's telling us this receptacle is good only for copper wire. Do not use aluminum wiring with this receptacle. Very, very important. Of course, when we were using aluminum wiring, we wouldn't want to use this receptacle with aluminum wiring. We would have to get a receptacle that said, not good for copper, good for aluminum. Fair enough? So we'll also see those markings on our receptacles. As you can see over here, we are looking at the hot side of a receptacle. You can see there is a screw here and a screw here. There's a little plate in behind the screw, and there's a little plate in behind the screw. If you notice, this plate, there's a tab in the middle that jumps over to this plate. Do you all see that? If we turn this around to the neutral side, you'll see it does the exact same thing. We've got our silver screw here and a silver screw here. Underneath it, we have a little plate, and again, they're interconnected with that little tab. We'll learn more about that tab in a short bit, but basically, when it comes to connecting this receptacle to my wires, I have, if we take a look over here, again, this is the hot side of my receptacle. We got a screw here, we got a screw here. I can connect wires here, or I can connect wires here. Whatever I connect here is going to go with that tab up to here, so I can bring power here and here. Making sense? Also in behind, so we got 2 screws here, and then on the neutral side, again, I can connect my neutral here or here. It doesn't matter, because if I connect it here, this tab is going to make the power go, or make the neutral go there as well. So they're interconnected. Again, there is a ground screw, and it's indicated with a green screw. When it comes to receptacles, every receptacle will have a ground screw. When we talk about switches, not all manufacturers of switches will have a ground screw on it. When we're talking switches, ladies and gentlemen, if there's a ground screw, always use it. If there is no ground screw, don't worry about it. And that's for switches. But for receptacles, there's always going to be a ground screw. Always use it. Fair enough? I'm going to come back to that little tab in a short bit. But again, let me show you again, if we look at the back side of this receptacle, if and when we are connecting wires, we can use these 2 screws here for my neutral, and I can also use this tiny hole here and this tiny hole here. This tiny hole here and this tiny hole here, they're interconnected. Fair enough? Now, when I use that tiny hole here, when I stick the wire inside, there's like little teeth in there. When I try to pull the wire out, the teeth are biting into it. I will not be able to pull the wire out. I would need to stick a little skinny screwdriver in that slot to open up the jaws to pull the wire out. Okay, that's what we would call a speedy way of making our connections. Again, we also have a hole here and a hole here for the hot side. So we have 4 locations that we can connect the hot, 4 locations where we can connect the neutral. Fair enough? Okay, so the wires that we would connect here, what do we need to do? We're bringing power to this receptacle, right? So the wires that are leaving this receptacle are going to the power source, Julius. Okay? If the wires we're bringing here is we're bringing power to this so we can utilize it. Making sense now? If I don't connect wires to this, I can plug whatever I want in here. It's not going to work. All right? And now those wires that are bringing the power to this, in this particular case, in a residential environment, the most common wiring we're going to use is non-metallic sheathed, American wire gauge 14. Most common of all of them is going to be American wire gauge number 14, 2 conductors or 3 conductors. Fair enough? In most cases, for convenience, this receptacle, we have 2. This actually is 2 receptacles. It's 1 unit, but we have a top receptacle and a bottom receptacle. Okay?
So we don't have single
You can
receptacles.
actually buy receptacles that is just 1 by itself.
Yes.
You could if you wanted to, but it doesn't make sense to, because if I'm going to occupy that space for a receptacle, I might as well take advantage of it, and I could put 2 in the same location. Now that we're understanding the anatomy of a receptacle, we're going to play with some connections. Of course, what I'm going to be drawing on the board, when we talk about drawings, we know them as blueprints. When we talk about blueprints for electrical, we refer to them as schematics. So what we're going to be doing now in a short bit is we're going to start playing with some of those schematics. And Mohammed, with some of those schematics, we're going to show us a variety of methods that we can connect our receptacle. And in doing so, we're also going to recap a lot of the information that we've already talked about. For example, I'm going to start off by putting an electrical panel over here. With your help, we're going to draw an electrical panel here to get a good understanding. Now that we're understanding a bit more of the anatomy of a regular receptacle, again, when we look at it, this is a Decora. It's exactly the same as this one here, traditional. Just the style changes. Again, the neutral is always the long slot, silver screws. Okay. When we look at this receptacle here, again, the neutral is the long slot, but it's also T-shaped because, ladies and gentlemen, years back, a 20 amp receptacle looked exactly like a 15 amp receptacle. So equipment that requires 20 amps, you would be able to plug it into a 15 amp receptacle very easily before. And if that equipment was overloaded, boom, the circuit would go off or you would damage your equipment. So equipment that requires 20 amps, when you look at the plug, it's going to be, the neutral is going to be L-shaped, which will not allow you to stick it in a receptacle like so. It just will not fit. So we need to have a 20 amp receptacle to allow for the 20 amp plug to go inside it. Fair enough? And again, it ensures that the neutral is on the right side and the hot is on the right side. So that being said, before we go any further with our schematics, I might want to take a few moments just to demonstrate the proper way of putting a wire into an electrical box and what we should do when we bring wires into an electrical box. Very, very important. So to make it easier for us to look inside this box, I've removed the one side, all right? And I'm going to just disconnect the wires in here temporarily. Actually, if I can show you right now, no, you know what? Let's do it step by step. I'm just going to remove these wires. Again, for our demonstration, I'm going to be showing you again our 2 most common screwdrivers. This is a Red Robertson. I'm going to just loosen this screw right here. When we look inside an electrical box, ladies and gentlemen, and what I've got right here in my hand is an electrical box most commonly used for receptacles and switches. Now, you'll see I was able to remove the side on this box Because if I do the same on another box, I can double it, triple it, quadruple it. I can make this a much larger box. For example, if you look in your own home, you might have 2 switches together or 3 receptacles together, whatever the combination is. This type of box, I can add to it. I can also buy boxes for the specific size. But in this particular scenario, I'm going to just take this off here to show us. Again, ladies and gentlemen, when we look inside a box, one of the screws has fallen out, but usually you'll have 1, 2 screws in the box itself, which we use. This is a metal box. That would be what we call a ground screw. Ground screw. The other one fell out of the box. Okay. Again, if we show you another electrical box, this one here, for example, is a common box that we use for light fixtures, also known as a ceiling box or an octagon box. Octagon shape. Again, when we look inside here, we have a ground screw here, and the other ground screw fell out in this box too, because I've been throwing these around a lot. That being said, a couple different versions of box. This is a light box, octagon box. Let's go back to our switch box. When you are roughing in your wires, what I like to do, ladies and gentlemen, I like to strip my wire before I even put it in the box. What I'm going to show you right now, ladies and gents, again, this is all tangled up, just to demonstrate, ladies and gents. Here is the non-metallic sheathing on our wire. Be careful when you cut this. We don't want to damage the conductors underneath, which is the reasoning why I'm going to show you what I'm going to show you right now. Of course, with a utility knife, I can come in here with a utility knife. I'm going to just score it in the middle of my sheathing, just like that. I can open this up now. I'm going to just strip this a little bit more for us. All right. I can cut this back. Always cut away from your conductors. You want to have a nice clean break like that. I'm just going to fix this ground wire now so it doesn't interfere with what I want to show you. When we're going to do a rough-in, you'll want to strip the sheathing off at least 8 to 10 inches, just like that. Okay? Then slide it into your box. So here we are. We're going to stick our wire in the box. I'm going to put it over here so we can see this very easily. We're going to slide this in. Now, a mistake that even a lot of electricians do not do what I'm going to show you right now. You see the sheathing on the wire. You never want to have a lot of sheathing in the box like that. That's just completely wrong. That is just occupying valuable real estate inside the box for when I need to make connections and so on. You see, eventually we are going to have to put this receptacle or switch in here as well. We don't want to be cluttering our box with all this sheathing. Instead, what you want to do is that sheathing, all it needs to do is, you can see there's this bracket, there's this clip at the bottom. We want to make sure that the sheathing just passes that bracket. So when I secure it, so the wire does not come loose in the box, when I tighten down on this, and again, no need to over tighten this screw that I'm tightening right now. There's no need to over tighten it, because if you over tighten it, even though the sheathing, see that sheathing is there to protect my conductors from getting nicked. Okay, we don't want to damage those. We just want to secure this bracket hard enough or tight enough that this wire will now not pull out of the box. We want to secure that wire to the box. So we just want that sheathing to come just past the bracket, the clip over there, right? Next thing, very, very important. The very first thing you want to do when you bring a wire into the box, again, I'm just going to move my conductors out of the way so we can see this a little bit easier. I'm moving the neutral and the hot out of my way. Next thing you want to do once your wire is in a box is we're going to put the ground wire around the ground screw. Fair enough? always, when we're putting our wires on screws to make a connection, always put the wire on your screw in a clockwise orientation. Always clockwise orientation. So I'm going to put this wire around that screw. Notice, let me just put this over here. I'm going to move these out of my way so we can see this a little bit better. Again, there is my wire. I'm going to try to do this so you can see it. I'm going to put it around the screw in a clockwise orientation. Never put your wire in a counterclock orientation, because when we go to tighten the screw, the screw tightens in a clockwise orientation. So if you put the wire on it from the wrong side, as you're tightening that screw, if the wire is in a counterclockwise direction, it's going to want to throw the wire off of the screw. Whereas when we go clockwise, the more we tighten the screw, the more that wire is going to get wrapped around underneath the screw. Look at how that ground wire is starting to go underneath the screw even more. Ah, fantastic. Now we have a good, solid connection. Always put your wire on the screw in a clockwise orientation. Next, here is my ground wire. This wire that's left here, we want to keep it there. This little section from here to here is what we call a pigtail. We've grounded the wire in the box. When we're going to be connecting our receptacle, we want to make sure that we now put the ground on the ground screw. So if we come here, clearly you can see the green ground screw. Again, when I'm going to put the ground on here, I want to make sure once again that I'm putting the wire on in a clockwise orientation. This is where I'm going to use my green driver now. All right. Just like so, ladies and gentlemen. And now that is connected. Of course, what we have left here now is my two conductors, my hot black, my white neutral. Hot black, I'm going to connect on the hot side of my receptacle. I can either put a loop on my wire, or I can, if I strip it nice and clean, you'll want to remove about a ½ inch of sheathing there. I could pop it right in the back in one of those little holes. Okay, once it's in there, ladies and gentlemen. I'm not going to put it in because I don't want to damage this receptacle. So I could either put it in one of those little holes. Here's another little interesting tip and trick I want to give all of you here. Here's my wire stripper. A little hidden feature on the wire stripper. You see these two little tiny holes? Well, I can stick my wire tip in that little hole, and I can now easily create a nice loop to go around my screw of my receptacle. So now again, this being the hot side, I can now back this screw up. I'm going to hook it on, clockwise orientation, just like that, and I'm going to tighten that up. And that is my hot connection. I want to show you another very important step. Notice when I strip the sheathing off of the wire, we want to make sure we have a good joint there. This sheathing, we don't want it to go underneath the screw with the conductor because you're not going to make good contact. And we also don't want to have a big gap. I don't want to have too much wire sticking below. That is a good connection right there. It's all protected nicely. Fair enough?
Yeah.
Now, that being said, all I need to do now is connect my neutral on the neutral side. Fair enough?
Yeah.
Excellent. So, on that note, ladies and gentlemen, we're now ready to start playing with some connections here on the board. Let's draw an electrical panel right here. Again, just going to make a little tiny panel here. We don't have to have a big one, just to give us a little bit of visual. I'm making this larger than it needs to be, just so we can see things a little bit easier. let's put here, for starters, our neutral bus bar. Here is a ground bus bar, a ground bus bar. We'll put another one here. There's my grounds. Let's do our hot bus bars over here now. We'll put one hot bus bar here. Again, I'm just going to make this very simple, ladies and gentlemen, just so we get a little bit of a visual as to what's going on. There's one there. Here is the other one here. Again, remember that they're just interlocking each other. Okay, just for, so we know what everything is there, right? Agreed? So let's put our main breaker over here. Here's my main breaker. We'll call that a 200 amp breaker. We've got our grounds. We've got our neutral. Okay, and then of course we have our hot and hot. Fair enough? Let's bring those main wires into the box. Of course, here is my ground wire. We're going to connect the ground wire. We're going to go to the, it's grounded now. There's my ground. Here's the neutral. Neutral is coming in. We're going to connect it over there. One hot wire. And the other hot wire. Now, here is my electrical panel. We'll put some breakers in there for a second. So actually, now what we're going to do, and to make sure we don't forget, ladies and gentlemen, that we always want to connect our ground inside a box, I'm going to draw a box as well so we can see the connections. Let me draw a box right here. Imagine, if you will, this is my receptacle. So that's my receptacle box. Let's put the receptacle in here now. That's my neutral side, the longer slot. That's my hot side. Okay, let's put now some contacts here. Here is the neutral side of my receptacle. Those are the screws. Let's put the hot side here. Those are my screw contacts. In the box, let's also put a ground screw in the box. And we're going to put a ground screw on the receptacle. Fair enough? Are we all good still, ladies and gentlemen? Let's connect this wire. Of course, let's also not forget that behind us, we also have these other connections. On the back side, we have the other connections for our neutral and our hot. So we'll just put those in this simulation right now, just so we remember they're there. Let's connect this. This being a common 15 amp receptacle, can somebody tell me what kind of wire do I need to run from my electrical panel to this receptacle?
14.
14. Is Godwin saying American wire gauge number 14?
Yes.
And how many conductors am I going to need to connect this receptacle?
2. Starts with the earth.
Remember, we do not count the ground. So we have 2 conductors, black and white. Fantastic. So let's connect a wire here. I'm going to just put a little wire on the bottom over here. We're going to make our connection over here. Let's call that American wire gauge, AWG, American wire gauge number 14. And we're saying 2 conductors. Fair enough? So let's start off with the simplest connection first. We are going to connect our ground wire onto the ground bus bar. Okay, here's my ground wire. I'm going to bring it over to the receptacle. First thing I'm going to do is I'm going to connect it to the ground screw. And then from the ground screw, we have the pigtail, which we're going to bring to the ground on the receptacle. Okay, so there's my ground. Let's do the neutral right now. Again, let's not forget, ladies and gentlemen, doesn't matter if you don't see this properly or not. We're using the color blue. You can't see that at all, but the color blue is our white wire, all right? Okay, I might want to just put that. Oh, we're good. Everybody understands I'm using this as my white. So here is the white neutral. What am I going to do with it? I'm going to connect it to the neutral bus bar. Here it is. And it's going to come down over to the neutral screws. Which screw should I connect this wire to? Top, bottom? Any suggestions?
Any side.
It doesn't really matter, does it?
Yeah.
Well, at this point, to be honest with you, it doesn't really matter. But just so I want to be helpful here for us, just again, when we work with electricity, we want to create some kind of flow and rhythm. So just like when you fill a glass up with water, the glass starts to fill up from the bottom and work its way up, right? So good little tip to help us with the flow of electricity, even though it doesn't matter if I go to the top or the bottom. Myself, I always connect to the bottom.
Okay.
So there is my neutral connection. Fair enough?
Okay.
Now, 14.2, I need to have a circuit breaker to turn the power on to this receptacle. What size circuit breaker do I need to use?
15.
Are you saying 15 amps?
Yeah.
Yes.
15 amp circuit breaker. So let's put our 15 amp circuit breaker right here. I'm going to use this right there for my 15 amp circuit breaker. Let's identify that as 15 amps. Fair enough? Are we good? So now we got our breaker in place. Here is my black wire. I'm going to connect it over here, and it's going to come down. Where am I going to connect it, ladies and gentlemen?
On the outside.
On the hot side. Am I on the hot side right now? Which screw would you prefer I put this on?
You prefer putting it on the downside.
Again, at this point, it doesn't matter if I go to this screw or this screw. But again, make it a habit of starting your connections from the bottom and working your way up. So now I'm going to connect this over here. We've connected the receptacle, ladies and gentlemen. Is this receptacle functioning now? Is it working?
No,
No.
Why is that, Ephraim? Why are you saying it's not working?
the breaker is off.
Oh, we didn't turn the breaker on. Oh, you see, Ephraim is paying attention here. So let's turn the breaker on. We turned the breaker on. Is it working right now?
Yes.
Yes.
We got the power. So now that the breaker is on, the power is coming down. It goes into the receptacle, and then it goes back to the panel on the neutral. Fair enough? So now we've got power, ladies and gentlemen. Excellent. That being said, this is a simple connection of bringing power to this receptacle. What we're going to do now to go over another scenario on how we can connect our wires is, what if we have, again, on a circuit, ladies and gentlemen, we don't want to overload a circuit, but at the same time, we want to be able to use power. So on a circuit, we can have a combination of lights, or lights and receptacles, or we can just have a whole bunch of receptacles. Whatever you're putting, I don't like to put more than 9 items on a circuit. Okay? Remember, we also have to be logical about this and see where we're bringing our power. What kind of equipment might be used in the room that we're bringing power to? See, we don't want to put too many items on one circuit, because if we put too many items on one circuit, it will be very easy to overload that circuit. Am I making sense? So to avoid us from overloading a circuit, this is where we want to say to ourselves, we only want to use 80% of what the capabilities of that circuit will allow us. For example, 15 amp circuit is going to be 15 amps times 120 volts, which is telling us we have a total capacity of 1800 watts. Well, we want to be proactive. What we put on that circuit, we're going to say we only want to use 80% of that. So what we're going to be wiring on that circuit, we only want to wire it to 80%, which is going to be 1440 watts. That way, at any given time, if somebody were to overload a circuit, we have a little buffer there before the power will actually go off. I might want to give us a great demonstration after we make a connection here. Okay, so now that being said, we now know the wattage in here and everything we want. Imagine on the same circuit, what I'm going to do is I'm going to put another 2 receptacles on this same circuit. Fair enough? This first connection that we're going to be making with these other 2 circuits is what we're going to call a series connection. For example, how many of you put up Christmas lights at winter, at Christmas time? Christmas lights. When you put Christmas lights, when you buy Christmas lights, Marco, the Christmas lights you put up, when one light bulb goes off, everything goes off. Ha!
That's correct.
Right. If you buy better Christmas lights, you can buy, so those lights that you bought, when one light bulb goes off, they are wired in what we call series. So when that one light bulb goes off, everything after it is also going to go off. But if they were wired in what we call parallel, one light bulb goes off, the other ones will still work. So when you look at Christmas lights, you might ask yourself, how come these lights cost so much and these lights cost so much? The ones that will cost you more, you're probably going to see are wired in parallel, which are going to be at least one light bulb goes off, you can find it, you can fix it, and everybody's happy. But if you buy lights that are in series, one light bulb goes off, everything goes off, and then you go crazy looking for the one that is no good. Okay? So this first scenario, what we're going to show you is wiring receptacles in series. So let's draw this right now. I'll put another 2 receptacles right next to this one. This connection we're going to be looking at is what we call a series connection. So let me just draw some fancy receptacles here. Again, for the first couple of scenarios, I'm going to be showing us the ground connection in the box too, because I want to make sure we don't forget to do this. So there's my ground, there's my ground, there's my ground. Let's put our neutrals in here. Neutral, 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 hot, hot. This is what we call a series connection. So what we're going to show you now is in series. We're going to start off, again, remember, ladies and gentlemen, when we go from box to box to box, we have to cut our cable in order for it to go from box to box to box. Some connections we're going to be working with today, sometimes the wire that are making our connections, they don't necessarily need to be cut. But because it's in a cable, we have to cut it. The wires that didn't need to be cut, we'll have to reconnect them with wire nuts. Well, that won't be the case just yet. Anyways, let's take a look here. Simply put, we're going to start off with our ground first, ladies and gentlemen. So from this ground screw, we come here. We're going to go to this ground screw and to there. From this ground screw, we come here and to there. Everybody's happy with the ground? Excellent. Let's go now with our neutral. With the neutral wire, what I'm going to do is I'm going to connect neutral over here, come down, and I'm going to connect it there. You see that? Then I'm going to come neutral over here. I'm going to come down. Oops. And we connect our neutral over here. So far, so good, right? Let's connect our hot wire now. So as you can see, we've got this wire connected here. I'm going to come here, my hot wire. To simplify things, I want to make sure everybody sees this. Here's my hot wire. Come here, go here, and I'm going to connect it there. Then from here, ladies and gentlemen, this is done in series, ladies and gents. So watch what happens. If this wire here is broken, what is working right now?
None of them is working.
Nothing is working. If this wire is broken, what's working now?
None of them is working.
None of them.
Nothing's working. Okay. What about this, ladies and gentlemen? This wire here is broken. Only the first one is working.
Okay.
Yeah.
What's working now? The first two. So there you go. This here, ladies and gentlemen, is a series connection. If you need to take a picture of this, take a picture of it. What we're going to do next is we're going to show us another connection, which we call parallel. So let me just remove the wires. Magic fingertips. No. Depending on the municipality you're in, some electrical inspectors will say you can use parallel or you can use series. In some municipalities, they say, we only want you to use parallel. In some, they say, nah, it doesn't matter as long as the connections work. So that being said, you will find in many cases, parallel is a better way of wiring things, but it can also start to clutter your boxes. We're going to show you why it will start to fill the box up too much. Now what we're going to do is what we call a parallel connection. I'm going to, again, ladies and gentlemen, this wire, I would have liked it to be on this side. So let me just come around here. I'm going to wrap these wires around just like so. So I can simplify our drawing here. Where did my neutral go? There's my neutral. Here is the hot wire. And let's put the neutral here. So again, remember the wire goes from box to box to box. So the connections I'm going to show you above each box would actually take place inside that box. Okay, so here we go. We go to the first box. What we're going to introduce now, we've mentioned this term before. Whenever we get a short piece of wire and we moret it and we go from that to our equipment, that would be called a pigtail. So in a sense, right now, off of this moret, I've got 3 pigtails. So again, whenever we have a little short piece of wire to make a connection, we call that a pigtail. So what's going to happen when we get to our first box, what we're going to do, of course, for the sake of understanding things here, I'm going to put a wire nut on all of my connections. But just so you know, as far as the ground is concerned, I can go directly to the ground screw and make my connections there. But just to simplify things, here's my ground wire. I'm going to put a wire nut. Fair enough?
Yeah.
And then that wire nut is going to go, again, imagine, if you will, that wire nut, just to simplify things here, I'm going to go here and there just like that. But we would have been going to the ground screw. I'll just put it like that for us. Again, over here in the next box, here's a wire nut for the ground. Okay, there's my wire nut. Next box, wire nut. There's my grounds are connected. Neutral, I'm going to put a wire nut. Okay. In the next box, a wire nut. Next box, ladies and gentlemen, a wire nut. And there's my neutrals. My hot wire, wire nut. Wire nut. And wire nut. This, ladies and gentlemen, is now wired in parallel. As you could see, my conductors are going parallel right through. And what I'm doing is I'm tapping into those parallel lines with pigtails to go to each receptacle. Now, that being said, ladies and gentlemen, if this wire is broken here, what's working? The second and third are still working, even though the first one is disconnected. This is disconnected. What's working?
The
First and
first
third.
one and the last one.
First
One and three.
are still working.
Yes.
All right. How about now? Second and third are still working. So this here, ladies and gentlemen, as you can see now, I have more control as to how my connections will work. So for example, when I wire in parallel, remember an electrician will do things in phases. They do what we call the rough-in first. We put the guts in the wall, and then we come back and do the finishing touches once everybody else has finished their work. Let's say, for example, we did the rough-in. Everything is connected in parallel. All we need now is the pigtails to connect to our equipment. Well, let's say the drywaller comes along and he forgets to cut the hole for the middle receptacle. Well, when I make my connections, this one and this one will still work. But then again, the electrician's going to say, hey, wait a minute, there's supposed to be another plug here somewhere. They covered it. Because he knows where he placed it, he can find it, expose it, and connect it. But if he doesn't find it, expose it, and connect it, at least the wires are connected and safe, and the power can still continue. Fair enough? So this is a parallel connection here, ladies and gentlemen. So again, the neutral and the hot are coming from the panel. So what we're doing is the power is starting from the panel. It goes to the first plug. It jumps to the next plug. It jumps to the next plug. And now this is where I want to help us understand a few things as far as the amperage is concerned. So in this particular case, we have 3 receptacles. It could have even been just 1 receptacle, or it could have been 5 receptacles. If we're plugging in the wrong equipment, regardless of how many receptacles we have, if we draw too much amps, or shall I say, if we're plugging in too much equipment, we're going to be using more power than we're supposed to. So with a 15 amp circuit, we know that the total capacity is 1800. So imagine if we had a radio and a coffee machine and maybe a heater. Well, each one of those requires more power. For example, I can have a radio, it maybe only needs let's say 10 amps, or shall I say 100 watts, 100 watts. I might have my coffee machine might require 600 watts. So I got a radio, 100 watts, coffee machine, 600. That is already 700 watts. If I have a baseboard heater and I want to plug it in on the same circuit, if that baseboard heater is 1,000 watts, that's already between those three pieces of equipment, 1,700 watts. We've went over our 80% safety capacity, but it's still going to work because we didn't reach the total capacity. Am I making sense? Now, what if that baseboard heater, instead of being 1,000 watt baseboard heater, is 1,500 watts? Well, if I have the baseboard heater on, the coffee machine, and the radio on together, that is going to be more than 1,800 watts. The power is going to go up because we're trying to get more power than is available. So the wire is going to say, "Oh, it's getting hot here. My butt is on fire." So the wire tells the breaker, "Hey, help me. I'm catching fire here." The breaker says, "Yeah, all right, let me turn everything off until we find out what's going on." Making sense there, ladies and gentlemen? That's where the breaker size, the amperage, is in communication with the wire gauge. So the wire can tell the breaker, or the breaker can tell the wire, something's not right here. Let's shut everything down until we know that everything is safe. So there is a scenario on how we can overload a circuit. Now, that being said, regardless if this is wired in parallel or series, that same wattage would be on that circuit. Fair enough? Like I mentioned before, depending on what you plug in, if you're plugging in the wrong equipment, you can easily go over the total capacity, even with one receptacle. But when we look at things logically in a house, what I do personally is I try not to go over 9 items per circuit. And then those 9 items could be 9 receptacles, or 4 receptacles and 5 lights, or 9 lights. Fair enough? Why don't I give us another great example with lights? Because I'm sure at one point or another, every single one of you has changed a light bulb. When we look at light bulbs, there are different sizes of light bulbs. When you look at a light bulb, it gives you a wattage. It might say 40 watt light bulb, 60 watt light bulb, 100 watt light bulb. Yes, no, everybody's made this observation before. So wattage is the power that that light bulb is capable of giving or taking or drawing. So now, that being said, another observation I want you to make. Those of you that have changed light bulbs in the past, have you noticed in the light fixture, usually you'll see a little sticker on the socket that says maximum 60 watts. You ever notice that little sticker in the light fixture that says maximum 60 watts? So you look at a lot of light fixtures, it will say right in the fixture, maximum 60 watts per light bulb. All right? How many of you in the past said 60 watts? That's not bright enough for me. I'm going to put a stronger light bulb in there. And Jamal, how many times have you said, I'm going to put a 100 watt light bulb in here. I want to see what I'm doing. And you put the 100 watt light bulb in and you go, everything is still working. Everything is good. I'm not going to tell anybody I put a 100 watt light bulb in here. And now your room is brighter, right? But what you just did is now you're drawing an extra 40 watts. So when we look at these lights, imagine, if you will, if we have, let's say, 10 light fixtures. If I have 10 light fixtures that all require one light bulb, when I put a 60 watt light bulb in that fixture, 10 times 60 is 600 watts. So I now use 600 watts of my 15 amp circuit breaker. Safety capacity is 1440. I didn't even reach half of my safety capacity, right? Let's double this up just a bit so we can understand my scenario a little bit better. What if we had, instead of 10 lights, 20 lights? Now 20 lights, if I put a 60-watt light bulb in each one of those fixtures, I'm now using 1200 watts, agreed? Which is still within my safety capacity. So if I bring that to my total capacity, I still have another 800 watts that I can utilize. But Jamal comes along and he says, you know what, I'm not going to put 60-watt light bulbs in my light fixture. I'm going to put a 100-watt light bulb. So now we had 20 fixtures, and Jamal ignored the fact that we're supposed to put 60 watts in the fixture. He puts a 100-watt light bulb. Now 20 times 100 is how many watts? 2,000.
2,000.
Boom, the power is going to go off. Why is it going to go off? Because he went 200 watts over the total capacity. So you turn the lights on, boom, the lights went off. Hey, why did the power go off? Because we're trying to draw too much power. The wire is saying, it's getting too hot here. Or the breaker's saying, I can't work under these hot conditions. I'm shutting it down. There's the safety capacity. So again, if we wire keeping in mind enough circuits for 80%, we're wiring in the sense that, you know what, let's not put too many items on this circuit. So we are always around 80%. So when we are looking at our 80% range, if Jamal should happen to come along and put a couple 100-watt light bulbs, hopefully we don't reach the total capacity and turn everything off. Making sense? So that is why we work with a safety capacity. We know there's a total capacity, but we work in mind that if someone should overload a light fixture or two light fixtures, hopefully it doesn't become a nuisance and we draw too much power where we have to continuously go turn the breaker on or continuously put the electrical under stress where something bad might happen. So that little scenario might help us understand how many things we might want on a circuit. Fair enough? Coming back to our receptacles, we've talked about series and parallel. Something I want to bring to our attention, and I'm going to introduce this now. How many of you have heard of a split receptacle? Or better still, let's start off with what we call a split circuit. So as you can see, ladies and gentlemen, you're going to want to make a note of this because today, not just today, but for close to 30 years now, it is code that in your kitchen, not the whole kitchen, but where your kitchen counter is, where you do all your preparation and cooking, around your kitchen counter work area, today by code, you need to have a 20 amp circuit. So you need to put 20 amp receptacles around your kitchen counter area. The rest of the kitchen, they can still be 15 amps, but around the kitchen counter, they need to be 20 amps. On top of those receptacles around your kitchen counter being 20 amps, they also have to be what we call a split circuit. Okay, so now not only are we putting a receptacle which is capable of drawing more power, but we're splitting that receptacle in half, where one half of the receptacle is on one circuit and the other half is on another circuit. Because in a kitchen, for example, and again, I don't want anybody lying to me. How many of you in your kitchen, around your kitchen counter, have that special plug where you want to plug everything in? The one that's in the corner, and you say, oh, I'm going to plug the toaster in there. Now I'm going to plug the blender in there too. I want to keep my phone charger plugged there so it's out of the way. How many of you do that? And how many of you, don't lie to me now, Marco, get those special plugs where you turn 2 receptacles into 6 receptacles? So these are receptacles, which we can also call sockets. This, see that breaker? That is what we call a circuit breaker. That circuit breaker is controlling these 3 receptacles. These 3 receptacles are all on the same circuit. Making sense now?
Yeah.
What will help us understand this a little bit more clearer, Godwin, is what we're going to explain right now, which we call a split circuit. Now, very important, when we are dealing with split circuits, there is a very important step that we need to do with our receptacle. If we don't do this, we are going to be making a big mess. So, because we're going to use 2 circuits now, what we're saying is we're going to get this receptacle and we're going to split it in half. We want the top to work on one circuit and the bottom to work on another circuit. So that means we're going to bring power to the top and power to the bottom. If we don't do anything at all to the receptacle and we bring power to the top and power to the bottom, what we just did is we now just brought, instead of 120 volts to this receptacle, 240. And whatever you plug into this is going to go boom. And you're going to get all kinds of smoke coming out of your equipment because the equipment that you're plugging in only requires 120 volts. So what are we splitting? When we look at the receptacle, remember this tab that we were talking about right here? I'm going to show you on the Decora receptacle. You can see there is this tab that goes from here to here, right there. This is the neutral side. Let's take a look at the tab on the hot side. There's that tab. What we're going to do, ladies and gentlemen, is we are going to get a needle nose plier. We're going to grab that. I can't grab it on this one. And again, even on this one here, you can see the tab. See that tab? What we're going to do is we grab that with our needle nose plier. I'm going to bend this back and forth. I'm going to split it in half. I'm going to break that little tab in the middle. When I break this little tab in the middle, for example, let's come back to these receptacles right here. I'm going to break that tab, and we only need to break it on the power side. So watch what happens over here. This is done in parallel, so this is going to work out well for us because you can see in parallel, I went to the bottom of all of these receptacles. When I break this tab, ladies and gentlemen, can someone tell me now what is working?
The bottom one.
Bottom one.
The bottom of this receptacle. Anything else?
Yeah, the other 2 is working.
So in this case, because I broke that tab, the bottom half of this receptacle is working, the top is not. From here, this is still completely working. This is still completely working.
Yeah.
I break the tab here and I break the tab here. What is working now, ladies and gentlemen?
All bottom.
Only
the
the
bottom.
bottom on all 3 of those are functioning. That is true. We've split those receptacles. Now, still in parallel, let me show you with a parallel connection how we can bring a second circuit into play. How can I introduce a second circuit here? What would I need to do to include a second circuit?
I have to bring another conductors, 2
We need
conductors.
to bring another conductor. to each one of these receptacles. And we also need another circuit breaker. Fair enough? Let's put another circuit breaker in here. That is another 15 amp circuit breaker because we're still talking 15 amp. Now, how am I going to bring that other conductor to these receptacles? Godwin is saying we need one more conductor, but if we are working in a residential environment, we are using cable. We're not. Remember, in this case here, because we're talking about residential, we're using cable, not single conductor wire. So if I'm using cable now, what would I need to do to bring that other conductor to all of these receptacles? Again, remember, we are talking about residential. Unless we are running conduit, we can't run a single conductor. We have to run cable. So what kind of cable am I going to run from the panel to these receptacles? Am I going to run another 14-2 cable?
Yeah.
I could run another 14-2 cable. But ladies and gentlemen, we have to be smart here. If I run another 14-2 cable from this breaker all the way to all of these receptacles, what I'm doing is, remember, we only needed one more conductor, but now I'm bringing a neutral once again, which is perfectly fine. I can do that. But now what I'm doing, number one, I'm wasting money on wire, because now I'm running extra wire. I'm wasting money on time because it's going to take more time to run a second wire. Instead of using two 14-2s, ladies and gentlemen, I can use a wire that has 3 conductors. So instead of using 14-2, what I'm going to do is I'm going to use 14-3. If I use 14-3, ladies and gentlemen, how many conductors do I have in that cable? 3 conductors. And what would be the color of those conductors? Red, black, and white. Fantastic. We've already used the white neutral. We already got our black power going to the bottom. Okay? What we're going to do now, ladies and gentlemen, is to the second breaker. Now that we're using 14-3, we're going to bring the red wire to that breaker. This red wire is going to come along here. I'm going to put a moret over here. From here to here, I can use black wire or red, but just to keep things consistent, I bring that wire there. In this box, a moret here. I bring it there. And over here, a moret here. And I bring it there. Now, this is what we call a split parallel connection. Everything is still in parallel, but this is a split circuit, which now the top of my receptacles are on that circuit and the bottom are on the other circuit. You see that there, ladies and gentlemen? That is a split circuit, what we just did there right now. This is a split circuit in parallel. Let's take a look at the same scenario using 14-3 once again, but we're going to do it in series this time. So in series, what we're going to do is we have to utilize, see, the thing is with this parallel, all these morets, they're going to have to go in each one of these boxes, and it's going to start to fill the box up too much. So this is where a series connection might come in handy. Let's show you series now. I'm going to just disconnect all of this stuff here. Okay, well, 14.3 in this scenario, because I've got split receptacles, it's allowing me to run one cable from the panel to this receptacle, to this receptacle, to this receptacle. I am using less wire, and it's going to cost me less money and time to do. The other option is 2 circuits. I would have to run 2 14.2s, 2 14.2s, 2 14.2s. Now I have an extra neutral, and it's also now starting to fill my boxes up too much. And I just run, imagine if you will, from the panel, these receptacles being 50 feet away from the panel.
Oh,
Now I just run 100 feet of 14.2 as opposed to 50 feet of 14.3. So we take this into account. Again, using 14.3, let's wire this in series now. I've got all 3 of these already split. Here is the ground wire. The ground comes here and jumps, comes here and jumps, from there and jumps. We've taken care of the ground. Again, keep in mind, ladies and gentlemen, all our conductors are in the same cable. I'm just showing you this in a quick fashion to show you the connections. Okay? Here is my neutral. Here's the neutral. It comes in. I go over here. From here, I'm going to come out over here with my neutral. I come in here. From here, I leave and I come in here. My neutral is connected to all 3 receptacles now. Agreed?
Yes.
Now, here is my black wire. The black wire is going to come in. I'm going to go here to that. I have to leave from this because that's the one circuit. I'm going to connect my other black wire here, and I'm going to come around to there. Connecting my other black wire in the back, come around, and I connect there.
Okay.
The red wire, where's my red wire? Here's the red wire. It's going to come in. I'm going to connect there. Then from here, I'm going to go to there. From the back of my receptacle, I'm going to go from here to there. Split in series. Now, ladies and gentlemen, because we have a split circuit, this is one receptacle. If this was not split, this receptacle, if that was not split, it would have the capability, the maximum wattage. I can use up to total capacity 1800, safety capacity 1440. Agreed? But when I split this, the bottom is capable of 1440 safety capacity, and the top is also capable of 1440. So I've increased, I've made it safer in that kitchen to use power at that one receptacle. See that? So now, when you come along with those receptacles, that octopus thing, and you plug it in, the top one now has 3 and the bottom one has 3, but they have the capability of a total capacity of 1800, and that has a total capacity of 1800, as opposed to just the 2 of them having a capacity of 1800. Now I've doubled up. I'm capable of running more power off of each one of those receptacles because it's a split circuit. Today, by code in a kitchen, we have to have a split circuit above our kitchen counter. Alrighty? Another very important thing that we're going to need around our kitchen counter if we have receptacles there. So that being said, we've now taken a look at a split circuit scenario. All right, so now what we're going to do here is I'm going to show us 2 other scenarios, ladies and gentlemen. So when we look over here, I'm going to just open up this image here. Hopefully we get some good images here. So when we look at cable, what we're looking at right here. Let's open up this image right here for us. The image on the left, both images here are non-metallic sheathed cable. This one here on the left, we have a black conductor and a white conductor. The ground we do not count. This is 14-2 conductors. The image on the right is American wire gauge 14, 3 conductors, red, black, and white. That is what we are bringing from the electrical panel to that receptacle. We are making the red wire go to one receptacle and the black to the other one. Does that clear things up there for us? I may want to just show us a scenario right here of a split switched receptacle. We can also do this as all on one circuit, or we can do it on 2 separate circuits. I may want to show you both scenarios. Let's take a look at what we're going to show you right now. I might want to just draw everything, all my connections from scratch. In this case here, what we're going to do is we're going to ignore the red wire for now. We're going to just take a look at a 14-2 connection. Let's put a receptacle right here. And here's my receptacle. Again, we have our hot connections, the ground, and let's put the neutrals in here. We're going to start simply again with the ground connection. Ground bus bar, we come along, we've connected the ground. Do the neutral next. Here's the neutral. Here's my neutral. Come along, and we've connected the neutral. Fair enough? Now, in order for us to have a split switched receptacle, we again need to break that over there. We break that tab once again. What we're going to do now, ladies and gentlemen, of course, I'm going to put a light switch over here. Here's my light switch. We have 2 connections over there. Again, if your light switch has a ground screw, use it. Here's the ground screw, and here is the ground in the box. Ladies and gentlemen, this is also going to be the first scenario where we are going to use our white wire as a power wire. Remember, we said 90% of the time, the white wire is always used as neutral. Watch what's going to happen here. I'm now going to bring the hot wire into this box. I'm going to put a moret over here. From this moret, I'm going to bring a pigtail to that bottom half of the receptacle. What's going on right now? What's working, Ephraim?
The bottom one?
Right now, the bottom part of this receptacle is working, and it's going to work all the time, but nothing is going on with the top.
Yeah.
Right? What we're going to do now, ladies and gentlemen, we need to run a wire from this receptacle to the switch. We're going to also run 14-2. What are the colors of my conductors? Black and white. So first, let's start with the ground. Here's the ground wire. Okay, now what I'm going to do from the same moret, I'm going to connect the white wire, and I'm going to bring it to the bottom screw. That's my hot wire. I'm now using the white wire as a hot wire. I brought power from here to the switch on the bottom. We need to make people know I'm using the white wire as power. I'm going to put black tape on it. So I'm going to put black tape here, and I'm going to put black tape here, so we can see in this box that's being used as hot, and we can see in this box that's being used as hot. Then we have the other conductor, which is black. It comes here, and I connect it over there. So now, when I turn the switch on, follow me now, ladies and gentlemen, with a different color. Here's the power. It comes in. When I turn the switch on, the power goes through the white wire. Switch gets turned on. It goes back on the black wire and turns the top switch on.
Yeah.
Power from here is going directly to this one all the time. That is what we call a split switched receptacle. I can control the top part with a switch.
Yeah.
The bottom part always has power.
Okay.
Fair enough?
Yeah.
Let's show you if I wanted to make this whole receptacle work with that switch. Well, simply put, if I wanted the whole receptacle to work with the switch, I'm not going to break this. And I don't need this wire here.
No.
Now, what's happening here, ladies and gentlemen, is the power comes to the box, goes to the switch, and comes back to the receptacle. Because that's not broken, the whole receptacle is working on the switch. When you remove the moret over here, well, of course, sometimes there may be power. Most of the times there will be, and that's the reason why we are isolating it. So sometimes we might just have a wire that we didn't bring power to that wire yet, and we just put a moret on it in case somebody energizes it. If somebody energizes it, we don't want anybody getting hurt or sparks happening and creating fires. So there might be just one wire that has a moret. But most of the time, when we see a moret, you see, for example, when I'm running my wire from this box to this box, I can't, of course, when we use cable, you can see, watch this if you can. Look at the neutral. In this case, you're probably not a good scenario. We'll be able to see this better when we start talking about switches. But that neutral, sometimes I will have the ability, for example, in a high-rise environment, when I use single-stranded or single-solid wire, if I'm smart, I can pull that wire through from box to box without cutting it, just letting the neutral go from where it needs to go, from point A to point B. But when we're dealing with cable, there's more than one conductor inside it. In order to run my cable from box to box, I have no choice to cut that cable.
Yeah.
So because I cut the cable and there's more than one conductor inside it, the conductors that didn't need to be cut, I have to reconnect them. And when I reconnect them, I'm reconnecting them with a wire nut. So depending if we're talking about the power side or the neutral side, the power, definitely there will be power. The neutral, if I were to take that wire nut off and touch it, I'm not going to get hurt because it's not the power. Okay? You'll only get zapped if you're touching metal and you touch that power at the same time, well, then you're going to do a little dance. All right? Ladies and gentlemen, you're going to get a link from me within the next 5 minutes or so for Monday morning. Have a great weekend. We'll see you Monday morning